Hello, welcome to another equipment repair video of me. This time it's this chonker and this chonker. This is all one part. It's like my bench is completely filled with it. It's an HP4194A, is it? Yes, just wanted to make sure. Impedance/gain phase analyzer. I got this one for effectively for free. Guy said, hey, it's not working, here, take it, I don't need it anymore, because, it's broken, it's trash, and I decided we'd go about trying to fix it this time. Now, full disclosure, I have already fixed it. Fixing these things is not easy, and I have the biggest respect to the people that actually manage to make videos about the repair while they're repairing it, because if I try to do it, I'll be sitting here like, yeah, how about that's the problem? No, okay, I have no idea what I'm talking about. So yeah, it's amazing to see people actually talk about what they're doing while they're doing it and it actually being correct. I'm not quite at that point yet, so I'm more or less just making a little report, what I did, how I solved the problems, what problems there were, how I figured out what the problems were, that sort of thing. So, first things we're going to do is we're going to actually have a look at the device, see what the problem was because I can actually reproduce it, and then we'll have a quick look at the hardware, maybe every board, I'm not sure, I don't really like pulling them out, depends on how motivated I am, but we'll have a look at the hardware, and then I'll talk about what issue there was, how I figured out what that issue was, and how I solved it, kind of. So, let me just readjust the camera so you don't have to look at my ugly face anymore, and we'll look at this. Also, before I forget, you notice I might have changed the camera around and then realized I wanted to say something more. I'll also be talking a little bit about the theory, but I want to say in advance that I don't really know all that much about how these things work. The basic principle, okay, that's sort of simple, but then as soon as it goes into the RFy section of things, I have no idea what it does, how it does it, so I'll just try my best to explain it. But if it's wrong, or if I'm explaining it poorly, please go into the comments and tell me about it, because I have no way of knowing. Alright, now with the thing zoomed in a little bit closer, we will want to turn the unit on and see what the fault actually is. Usually, if you remember my last repair, I would say use the thing, try to figure out where the problem could lie as much as possible, just from that, so you don't have to dick around with a circuit, especially because for this thing here the service manual is in a very, very poor quality. The PDF is scanned at like 10 dpi and the schematics are unreadable. We'll get to that later. But because this thing has already been repaired by me earlier, and I had to sort of fake the issue, we can't really do that because now it's a measurement issue instead of an equipment issue. So we will be skipping this step for now. But again, remember, if you repair something, use the thing, try to use different functions of it, do anything you can to isolate the area of the instrument where the fault could be, making it much easier to look at the circuit, because you don't have to look at the entire circuit, you just have to look at the circuit of just the very specific part you isolated the fault to. Anyway, without further ado, let's turn the thing on. And you might hear why I didn't have it turned on before, because the fan is fucking annoying. So the fan of the main unit is actually broken and I've disconnected it because it's like, it's a dumpster fire, it's completely dead. The fan you're hearing right now is of the second box, which is the front end. Anyway, you can already see the issue. It says down here, Bridge Unbalanced. Not sure if you can see that. Let's correct a little bit. There you go. Bridge Unbalanced. Now, this fault... Just give me a second. There we go. Quiet. This fault is actually fairly common. It can happen when somebody is a bit enthusiastic connecting things to it, like for example a charged capacitor, or even a device that feeds power back into the unit. It could happen just from old age or from a variety of different things that I don't even know. as it likely did in this instrument. So we're gonna play around with the thing a bit anyway, and you can see the measurement is weird. If we try to actually run a measurement, it always complains no matter what frequency you're at. We can try setting the frequency to, I don't know, 10 kilohertz, and it might actually work. So if we go, I don't know, span is fairly small, but you can see the frequency up here. So that's 16 kilohertz, 15 kilohertz. Nope, hold on, there you go. You can see it is measuring something. The measurement is completely unstable. We currently have nothing connected to the output. Or, well, would have nothing connected to the output in the original way we're testing this. And no matter where we're measuring, we're always getting some really weird readings. They're jumpy and stuff, but sometimes you can actually get it to do a measurement which seems reasonable. So, there you go. So sometimes it actually does a trace without any beeping. No problem detected, no complaints. Let's see, it just said AC current overload there for a second, which is an unrelated fault, by the way. So you can trigger it and you might be like, oh, you know, the Bridge Unbalanced fault is gone. Maybe it's actually something with my measurement setup. You change things around, and then sometimes maybe it'll do it, maybe not. There you go. And then you'll just get that Bridge Unbalanced error again. Now, in order to understand what this error even means, we'll have to look at the operating principle. And for that, I'll switch over to the whiteboard. Maybe. I'm not sure. Alright. It feels to me like the camera is a bit too close to me, but on the video it looks good. So if it's too close, well, I don't know. Maybe I'm going to just shrink me down. No, obviously I'm not. So first of all, let's talk about how impedance measurement even works. Well, in general, and then a bit more specifically in the case of the instrument that we have here, because it does some fancy stuff with the current measurement, but we'll get to that. So first of all, very simple, the actual impedance of a circuit can be given by the current that flows through it as the result of voltage excitation. You could do it the other way around. You could apply a fixed current to the device under test and see what voltage appears across it, but it's hard to do because current sources are hard. They're just not as good or as easy to build as a voltage source. So voltage sources are what is commonly used. For example, if you use your multimeter to measure resistance, it's the same thing. It applies a voltage and sees what current flows through it. At least I think. Correct me if I'm wrong.
Wrong.
So in this case, we would have a device under test here connected to a voltage source, and just all we'd have to do in order to measure the impedance of it is know what voltage we're applying to it and know what current is flowing. Now, because impedance isn't just current or just purely resistance, we also need to see the imaginary part or the phase of the impedance. We will also need to measure the phase of the current that is flowing, but when we know that, we could also calculate the complex impedance of the circuit, and we're done. Seems easy. Now, there is a problem, however, and that is, how do you measure the current? You might think, oh, you know, just open the line here and put an ammeter there, and there you go. Now you can measure the current. However, your ammeter circuit, which is the circle on the outside, has a resistor and a voltmeter in parallel to it. What this, however, means is that you will, of course, have a voltage across this point. Otherwise, your ammeter couldn't actually measure what current is flowing. That voltage here will get subtracted from your supply voltage, and then the voltage across the device under test is not what you're actually applying to it. You think, oh, hey, we're putting 1 volt onto this thing, but if you have a 0.5 volts drop across your ammeter, well, you only have half a volt across your device under test, and if you use the voltage that you're supplying to it in the impedance calculation, you're going to get a wrong value. So what you could do is you could convert your ammeter to a circuit like this, which is also an ammeter but does not have the issue of a burden voltage. Instead of using a resistor and measuring the voltage across it by putting it in series, we effectively use an operational amplifier, or any amplifier if you will, to create a virtual ground at this point here. What does that mean? Well, an operational amplifier will always try to keep these two inputs at the same voltage. If there's a differential voltage across these things here, it will amplify it and apply it to the output. The inputs say in which phase or in which polarity, if you will, that change occurs. So if the inverting input signal is too low, then the output will be set high, or will rather increase, because it's linear and not a digital circuit. So what happens here, if a current starts flowing into here and the output is at ground potential, then in theory, if the amplifier wasn't there, then the resistor would just be in series. However, current starts flowing in here, the resistor starts having a voltage across it, for example, say 1 volt. If this thing here is at ground potential and that has 1 volt across it, then this thing here will be at 1 volt potential as well. And the op amp will be like, oh no, we have a voltage here, let's do something. The voltage here is 1 volt, inverting input. That means in order to equalize the voltages there, it will drop the output voltage negative. So this thing here will go down to minus 1 volt. I would rather think of this thing as an operational amplifier, if it is ideal, always keeping its inputs the same. So this voltage here is going to be the same as this voltage here, aka ground. That's why it's called a virtual ground. But no current flows into the pin here. So if we have a look, here we have our dot current, here we have the shunt current, and here we have the input current of the op amp. Sorry, it's a bit hard to read. Wait. So if you then look at the currents that are flowing in this node, remember they all have to be 0 when you add them together. Then we have the current from the device under test flowing into the node, and out of the node the current into the operation amplifier, which in an ideal amplifier is 0. So this thing effectively isn't there. And then we have the current flowing out of here. That means all the current flowing into here has to flow out of here because it has no other place to go. It flows through this resistor and then results in a voltage across it. And the op amp will do whatever it has to do, again, to keep these two things at the same potential. And that results in the voltage on the output being pulled low until this voltage here is the same as that. So the voltage across this resistor here is still proportional to the amount of current flowing through this circuit, but unlike in your normal ammeter circuit, this thing is not effectively in series with your device, because this virtual ground means that to the device under test, this entire circuit looks like this. It is just a ground. Now you might be like, oh wow, this is amazing. Why don't we use this for anything? Why do we need like a massive multiple $1,000 instrument to do this when it's so simple? Well, of course, it's never that simple, is it? The problem is that this operational amplifier here is obviously not ideal. The main problem with operational amplifiers is, first of all, that they do have an input leakage current. It's not that great, but it's not negligible, especially if you want to measure a very low current. So for example, if you have nanoamps going into here from your device under test, then this thing here sinking even just 1 nanoamp will have a significant offset, will add a significant offset to the entire reading of the current. Of course, also the gain of operational amplifiers is not infinite, unfortunately. It would be cool sometimes, but obviously it isn't. And that means that at some point there will be a tiny bit of a voltage in between these two things. The higher the gain, the smaller the voltage in between these 2 points will be, because even a tiny voltage will be amplified by a massive amount and result in a large voltage swing here, which is able to compensate the voltage drop across the resistor. But especially as the frequency increases, the gain of the operational amplifier will drop further and further until at some point it doesn't have any gain anymore at all. And especially if you want to measure 40 megahertz current, which this thing here can actually do, it is extremely hard to build an amplifier that can do it. And not only do you need to have an amplifier that can amplify 40 megahertz of current, because only that would be relatively easy. You could, for example, down convert and do all sorts of funky stuff, but no, you actually need to go from 100 hertz to 40 megahertz. And a high gain amplifier across the entire bandwidth of that input signal is just very hard to achieve. So the HP engineers thought, how could we measure the current in another way? And they came up with a very interesting solution. Let me draw that now. Sorry, I had to move the camera around a little bit because I think I was standing in front of the actual drawing sometimes. But back to the theory. If I could find the pen. So what the HP engineers figured out is that you could effectively use a second controllable voltage source at this point here to act as your operational amplifier. In effect, this thing behaves in exactly the same way. It creates a virtual ground at this point. Let me just get a nice pen so I can draw that down. We will once again get a virtual ground. So this node should always be at 0 volts. And in order to achieve this, it will control this voltage source to provide the same voltage that an operation amplifier would if one was in this part here. But instead of using that, they actually put here a null detector. What this does is, if the voltage at this point here is high, do magic to decrease the voltage that the source here is outputting until the voltage drop across this resistor is compensated and this node is at 0 again. Behaves more or less in the same way that the operational amplifier did, but because you just have a controllable voltage source, or in the case of this thing, because we actually need AC, a voltage controlled oscillator with an adjustable phase, you don't actually need to have some super high gain amplifier. You just need to be able to check, is this 0? Yes, no. You might actually make the argument that this is also an amplifier, but overall it behaves much more simply, and this is somewhere where I have no idea really what I'm talking about. I'm just sort of saying what the service manual talks about, but this is apparently a lot easier to build than just a high gain amplifier. So once again, just like with the operational amplifier, the voltage at this point here will always be 0, and the voltage here adjusted so the voltage drop across the resistor is compensated. That means the voltage across this resistor here will be proportional to the current through the device under test without effectively having that thing in series. Now there is one added bit of difficulty regarding the output generator source. Well, it's not the output, the feedback generator source, whatever you want to call it, the source other than the reference. And that is that, although it might be fairly simple to just create a DC source if you wanted to only measure resistance, it's not that easy, or at least not cost effective, to build a full second oscillator that could be completely independent from the primary one if you want to do it in the AC domain. So what instead HP is doing is grabbing the signal from here, sending it over here, adjusting the phase. Well, let's just draw that in here. I have no idea what the proper symbol for that is, so we're just gonna do a phase adjust and a variable gain amplifier in series with that, which is controlled by this. So, hold on. So instead of having an entirely separate oscillator on the output, you just take the reference or the source signal, adjust the phase of it, the phase of it, and amplify it until this point here matches, because of course the device under test will not change the frequency of the signal, and thus we don't need an entire separate oscillator for it. But there is one more little problem you will get when trying to build a setup exactly like this. By supplying the voltage here and only measuring the current that flows through your overall test setup, you also measure the impedance of your test setup itself. So if you have, for example, 100 meter leads in between your voltage source and your device under test, they're obviously going to have a significant resistance as well. Now, of course, you won't have 100 meters of cable between that thing and your device under test usually, but we're talking high frequency stuff here, 40 megahertz, kind of high frequency. For me, it's super high frequency because I'm doing power electronics. For RF Voodoo engineers, it's going to be like DC, it doesn't matter. But these leads here will have an impedance by themselves, and you actually want to calibrate that out, or you want to be able to ignore that for your measurement. So what do? Well, instead of just saying, oh hey, I'm supplying 1 volt to it, you measure the voltage. So as close as possible to your device under test, you will connect a voltmeter. Again, every little bit of connection in between your device under test and the voltmeter will add to the impedance measurement. So if possible, you literally just connect it straight to the actual resistance element or impedance element, whatever that may be. And a similar thing happens here because we have a null detector that more or less detects the voltage at this point, not just more or less. It detects the voltage at this point and tries to reduce it back to 0. We somehow need to compensate for the voltage drop across the cables here as well. And once again, voltage drop across cables we can compensate fairly easily by, instead of connecting that thing here, connecting this directly at the device on the test. So right there. Now all of the current that goes into this cable here obviously has to come out here, so it doesn't matter if we have the second voltage source connected somewhere far away from this, but the voltage measurement happens exactly at the device on the test. So although we are actually adding the cable resistance or cable impedance to our test impedance, we could calibrate this out because cables stay the same and only the device on the test is actually measured again. Now, how about that bridge unbalanced error we were getting? Well, all that means is that the instrument is telling us, hey, I am unable to zero this point here. So if the bridge is unbalanced, then we don't actually have a 0 here and, for example, have an open in this wire here. At that point, all of this circuitry might be working perfectly well, but because it is not actually able to drive any current at this point here because it's open, so actually here it could set anything, any voltage, but because this is open, the only current flowing at this node here is going to be the leakage current into the 0 detector, which is obviously not enough to compensate the measurement current, and the voltage here will be other than virtual ground. At that point, there's a separate detector in the null detector that says, hey, something is going wrong. We've been at a voltage other than 0 at this point here for far too long. I don't know what it is, but the bridge is unbalanced. And something is wrong, we're in an error condition, better tell the user. And in this situation, it tells, hey, bridge is unbalanced. Sorry about the slight change in drawn image. I had to re-record a section because my camera app is going a bit nuts. What I was just saying is what could that bridge unbalance error be caused by? Well, we've already seen if this part of the wire here is open, it would be unable to balance the bridge. But of course also a fault in the null detector could result in this. So if this thing always told the amplifier, hey, go full on, give all you can, even if there was basically no current flowing through here, then you would have a voltage at this point. Or if that thing always said, hey, slow down, we're already way off, don't output anything, even when there was a voltage here, it would of course also result in a bridge unbalanced error. Now, in theory, it could also be that, for example, the power amplifier is broken, or the phase adjuster is broken, or any number of these things. It can, however, not be the source side, because in this case, the source side has actually got some supervising circuitry, which makes sure that there's an output, that the output is correct, or at least kind of correct. And an error here would not cause that, so the fault would be anywhere around this section here. So the problem could be in the null detector, it could be in the phase adjust, the controlled amplifier, the power amplifier, or in theory in the resistor as well. Now how we figure out where exactly it is, we will talk about once we're actually looking at the instrument itself, which we're going to be doing now, just looking at which circuit does what is where, and that sort of general stuff. So let's change the camera angle and look at it. Wait, sorry, magic doesn't work like this. I have to do. There we go. So let's first of all have a very brief look at the digital control section. One thing to keep in mind, you do actually want to unplug things, obviously, but you definitely want to unplug and not just switch the instrument off, even if it has a real clank and power switch. Okay, that was a very bad accent. Because, especially with RF gear, there's always the possibility that there are going to be some standby voltages, for example, for oscillators, frequency reference oscillators. They do like to be kept warm. So there is a chance, for example, this thing here does have a high stability option over here. I'll show you that later. That would always be powered, and that even with the main power switch off, there will be some voltages in here, which is of course not a state in which you want to play around with it. So everything is off, it's unplugged, it's had some time to discharge, and even these things back here where it's actually saying, yo, this part is live, don't touch it, they're discharged. We won't be having a look at the circuitry of the power supply because it's just a power supply, but we will instead have a look at... Okay, hold on a minute. I usually would have been doing the teardown and explainer section in this part of the video, but honestly I didn't really feel comfortable talking about all the sections because I, as I said, don't really understand the RF portions of that anyway, and would have just been saying, hey, there's some circuitry here, great. So there is actually another really good video of a teardown of an 4194A. I can never remember the number of this instrument on YouTube. I'll link it here or here, I don't know, wherever, there in the description for sure. If I forget about it, just remind me in a comment. But I'll link it, go have a look at that. There's a detailed look at all of the circuit boards. Just go have a look at that. I'll continue on with how I fixed the issue, or how I isolated the issue, what I did to fix it, and a bit of playing now. So how did I actually diagnose it? Well, there are a few steps in the service manual that allow you to check the null detector as well as the feedback oscillator, you might call it, I'm not sure. This one. And basically what they do is they tell you to connect the output of the high side to the feedback of the low side, not the current output, but the actual measurement. Sorry, not the current input, but the actual measurement input. And then look at some signals. So there are some test points on this thing here, which allow you to check if the null detector is working properly, which it was. Then you are supposed to disconnect the input to the power amplifier, so this thing here, from that, and see if you're getting a signal on this point with the correct parameters, which I was. And that tells me that everything starting from the null detector through to the feedback oscillator was actually working correctly. So no faults in this section here. That means the fault had to be on the other side. Also, at that point, I realized that the low current input actually was at a fixed voltage all the time. And it was also a fixed DC voltage, not just some AC signal, which meant there had to be some fault in it. If you just hooked the scope up to it, you had a steady plus 2.8 volts, I believe, on the low current terminal, or L cur. I'm not sure if that's supposed to be low current or whatever, but I'm gonna just call it low current. And that sort of made me isolated to this section. Again, this is the input signal to the amplifier. This is what you check to be okay when you measure the output of the feedback oscillator on the other board. That goes in here and goes into this section here, which we'll have a closer look at now. So unfortunately, this is the state in which you get the service manual. Well, not exactly this state. Rather, you can see that all the wires are like really pixelated and there are things missing. You can't read any text. So what I decided to do was to just quickly reverse the circuit, go through beeping everything out, measuring some values so I could actually get a feeling for what is actually connected where. And if you were just to focus again, there we go. This is the actual power amplifier section of the feedback oscillator. So into this side here, we get the phase shifted and amplitude corrected reference signal, which we then need to amplify to come out here and will then be connected to the resistor. So on this side of the schematic, you would have had, if you had printed it, a bank of a few different feedback resistors to select the ranges. So here we are effectively just looking at this portion of the schematic where we have actually isolated the fault to. So what this is a differential amplifier in series with another differential amplifier for higher gain, in series with an output power stage. Sorry if the terms are wrong. I have more or less no idea what I'm talking about with analog. This is just sort of what I ascertained from actually working on it. So this thing gives it a bit of initial amplification. Then the second differential amplifier stage here, which actually looks really weird because you have no load resistors, no obvious load resistors anywhere. They are actually down here, one outside the can and one here inside the can. That are this one here and this one here. I have no idea why this one is outside and this one isn't, but anyway. So you have a second differential amplifier stage here, giving it a bit more gain. Finally driving this power stage here, which interestingly enough has some electrolytic capacitors here. I have no idea what's going on with those. It's very weird. It's actually those two guys there. And what was broken in my unit, you might have already spotted it earlier, are these two transistors. So those would have been here, but you see there are some TO92 packages instead of the TO, whatever the metal cans are. And that is because, well, I've replaced these. Now, you might be like, oh, very nice. You found some matching replacement part with matching parameters, gain, frequency, and stuff. No, these are just 2N3906s, like just bog standard junk pin components that I just had around. I just put them into here to test it. Now, because this thing is running with a feedback configuration, it's actually not that bad, because even if the gain is different, the input signal will just be a little bit higher. But of course, especially in the higher frequencies, with the gain that this stage here has to create, you will have issues with phases and amplitudes coming out of this thing here just not being what they should be, because the original transistors had a transition frequency of, I think, 1.3 gigahertz minimum, so even higher probably. Whereas the 3906s have a transition frequency of only 300 megahertz, and these things are cheap junk pin ones that I just had laying around, so they might not even be that good. But it is good enough for testing this, and replacing these things here actually fixed the problem. Because these things being faulty prevented the power amplifier from actually outputting anything, opening the bridge loop at this point here, and causing the bridge to go unbalanced. So once again, very quickly, I tested the output of the null detector here. by verifying the signals as they are given in the service manual on page
8-158 or page 423 in the PDF.
Then I verified the feedback oscillator. Again, I'm not sure if the name is correct, but this part here, or the output of this part here, by also following the steps in the service manual on page
8-153 or page 418 in the PDF.
Is it at all noticeable that I had to put this in post? No, I'm sure not. And that allowed me to narrow down the fault to the power amplifier here. Checked which transistors were broken. I literally just checked, is there a signal coming out of these things here? So the outputs are this one here and that one here. Is there a signal on these two lines? Yes, there was. Is there a signal coming out of the PNPs here? No, there is no signal coming out of the PNPs. They're going to be faulty. Interestingly enough, both of them failed. I'm not quite sure why that happened. It could be that the entire biasing of the circuit just went through the roof, or just completely off the rails, whatever you want to say, when one of the transistors failed, and that killed the other one. But it is still suspicious that both of these things would fail. That two of the same transistor would fail in the same circuit right next to each other without any external cause. Now, while we're looking at this circuit, there's also this part here, which looks a bit weird. This is for zero/drift correction. It's just an integrator that integrates the low-pass filtered output. So the low-pass filter of this thing here basically just gives you the DC content of this signal, or at least a very low frequency AC content, and integrating that will give you nothing if this is properly centered around 0, but if you start drifting up or down with your sine wave at this point, then the integrated value here will change, and that gets fed back through this line into one side of the differential amplifier, effectively correcting for that drift again. So now that I have given a very brief explanation of what I fixed, we're actually going to just turn the thing on and have a bit of a play with it. Oh, and also I was just wanting to show you the fan, because it's terrible. If I just switch on the unit, and plug the cable back in, just move everything nicely, there we go. You can see the fan whirring away, and I think the sort of very obvious peak in the audio spectrum is because it's in front of this weird baffle here. That, I think, makes it act a little bit like a siren, which is weird. And the instrument is complaining because I still have my fake bridge open, or unbalanced bridge thing here. Just disconnect this. It should stop complaining. There we go. So now that the instrument is working again, I think we could do a couple of quick experiments with it, because it is very cool. Now, if you've never actually seen what this thing actually is used for, or what you can use the thing for, it is basically one of these things on steroids. This is an LCR meter. It's what you would use, for example, for measuring the value of a capacitor, seeing if an electrolytic capacitor is still within spec in terms of its ESR, or many different things. So for example, you have your electrolytic, you're like, oh well, is this still okay? You just take this thing, set it to C, connect it. Sorry about showing this so well. So you just connect it, and then you see, oh well, it's weird. You can set the frequency at which it's testing. So there you go, 470 microfarads. You see the ESR. And again, you can test it at different frequencies, but the frequencies are fixed. So this thing here goes 100, 120, 1 kilohertz, 10 kilohertz, and 100 kilohertz. But maybe you want to measure at a megahertz, or you want to measure at 120 megahertz or something. That is where the proper analyzers come in. Now this thing here goes up to 40 megahertz, so you can actually apply 40 megahertz waveform and see the phase and the, well, what is that actually? Just measure the impedance, the phase and the amplitude of the current. I think that is what it's called. Anyway, you can do that with this thing. Of course, this is a lot smaller, but again, it doesn't actually measure on such a large frequency range. And also what this thing cannot do, which is actually one feature we're going to be taking advantage of, this thing cannot apply a DC bias. So for example, you might want to measure, hey, I have a capacitor which is going to get a little bit of AC, but it'll be pre-biased with 20 volts. Does it still behave the same way that it does when I simulate it at 0 volts? So for example, ceramic capacitors are known for being very poor, depending on the dielectric type. They are known for being very capacitance unstable as the voltage increases. Sounds weird, but I'll show you in a second, because again, this thing can actually measure that. So for example, you can apply a DC bias to the thing. Again, the frequency range is larger, and also you can do frequency sweeps. This thing cannot just test at a set of fixed frequencies. You can actually have it sweep all the way from 100 Hz to 40 MHz and actually see the change in the impedance over frequency. Again, this thing cannot do that either. Now, of course, this is a lot more convenient, but this thing can do more. Now, you can see that we have these very interesting looking test clips which are out of focus. I'm sorry about the focus, by the way. I don't know, the app for some reason doesn't do continuous autofocus, and I have no idea how to set that. So you'll have to just live with me maybe being a bit out of focus. Yeah, but hey, at least it's 4K, right? Okay, I just checked and it was quite dark. Sorry about that. We have these interesting looking clips. Those are for Kelvin measurements. Just what I said before. We want to actually measure the voltage we're applying to the thing and the voltage that, well, the 0 point exactly at the lead. And for this we use these Kelvin clamps. They actually have two separate... Let me actually focus, sorry. There we go. They have the two parts of this separated and also connected separately. So one of these things here is the current source and the other one measures the voltage. And same on the other one. One is the current return and the other one measures the voltage that occurs across the device, and you can just hook it up. It's hard to do on camera. And then see the ESR and the capacitance value of your capacitor. Now, of course, you can also measure resistors with this. For example, a high power wire wound at 120 Hz apparently behaves like a very large capacitor. That's just because the phase of the current is weird. You can set that to R. Okay, that's measuring R and the equivalent series resistance of R. But yeah, you could, for example, check, hey, I have a 100 kilohertz signal. Is my resistor still going to be a resistor? And you can see, no, it's not. It's actually become an inductor. So instead of playing around with this tiny and boring little thing, let's go and play around with the real deal back on the bench. This sort of a measurement setup with Kelvin measurement is also, of course, required for the big boys. And there you can get so-called test fixtures. Now, this is a very simple one. They can go up to some really, really expensive measurement setups with lots of gold and everything gold plated for example, actually measuring with very high accuracy resistance elements on semiconductors or other very high accuracy resistance elements. There you actually have like little needles, I would almost call them, that you could put onto the resistance element and then set more tiny probes directly onto it. Those could cost thousands of euros. This is just a fairly simple one. You have the connections for the bridge here. This is just to prevent you switching the switch on the front of a unit for cable length. Apparently you can set cable length, probably just for compensation. But yeah, this is there so you can take your device on a test, which for us is going to be... Oh, there we go. A set of ceramic capacitors, 10 microfarads, two different dielectric types. You can see, I'm not sure which ones this is actually, probably X5R or X7R. But yeah, two different ones. And we're gonna do a biasing sweep. So we will check how the capacitance changes with the applied DC voltage across it. So I'll connect these up and we'll have a look at the front of the unit again. Okay, so let's see if I actually managed to get the front panel in focus this time. Hard to see that on the small screen again. Sorry about the focus throughout the video. But as I said, we would want to have a look at a bias sweep. So I'm going to set that up now and then we'll have a look at it. So first of all, currently we're just doing a normal frequency sweep from 0 to, well, from 100 Hertz to 40 megahertz, as it says down there. And it is plotting the resistance and the phase of the current. So you can see 7 ohms, 7.5 ohms at 30 degrees. Now, of course, we want to be measuring capacitance. So what we can do is we can say function, impedance, C series and R series. And there we go. Now we still need to tell it to auto scale those two measurements. There we go. We can see, well, we have -1 nanofarad and 6 ohms, but that is at a frequency of 20 megahertz. And I have to say, at these high frequencies, I suspect the fix that I did with the 3906 is going to be impacting the accuracy of the measurement. So instead, we will be doing a measurement up to 100 kilohertz. That should already be enough. There we go. So you can now see capacitance. It says 6.8 microfarads, 6 ohm series resistance. And we can scroll through, measure this at a few different frequencies. And especially down at the low end, you can see that the ESR actually changes quite significantly. There you go. Now, I'm not sure if that's actually real. So that will be at 100 Hertz. We have 9 microfarads and 15 ohms. And then at like 5 kilohertz, we start dropping down 7.2 microfarad, 6.7 ohms. Again, I'm not sure how reasonable that is. This thing isn't calibrated in any way, and it literally just has a completely modified output stage. So all bets are off, but you can still see sort of the tendency of the, of the measurement. Tendency, is that the right thing? But you can still see the measurement roughly doing what I would expect. So again, let's set it up for a bias sweep. So for that, we can do sweep, more, and set a DC bias. Then instead of the start command changing the start frequency, it now changes the start bias. It's a bit hard to read potentially. Let's maybe make that a bit darker. There we go. It says 0 volts here. Great. So at this point here of the graph, we will be starting with 0 volts bias. And then we can stop that at, it's a 6 volt capacitor. We're just going to stop that at 10 volts because why not? And we still have to auto scale the readings. I think actually we can hide the ESR. We don't care about the ESR. And now you can see that the capacitance actually significantly decreases with the bias voltage applied. So we are measuring, actually we have to say spot frequency that is at 100 kilohertz. We're just going to set this to 50 kilohertz. What just happened? Did something else just break? Alright, don't worry, it's not broken. At least I don't think. So what I think happened was that where I said, you know, the capacitors are only rated for 6.3 volts, let's just give them 10 anyway. I might have done that yesterday and given both 40. So there's a fairly decent chance that they're just both dead. And there's a short. And that somehow results in the thing not being able to actually balance it because effectively we are measuring a short with DC bias applied. I'm not sure. It shouldn't cause any trouble, but especially because it should actually say DC current overload instead of bridge unbalanced. But anyway, I've just switched over to a different capacitor. This is now 47 nanofarads. And yeah, it's better. Now you can see that at 0 volts bias, we're at 48.23 nanofarads, so that's perfectly fine. But as the voltage increases, the capacitance drops off quite significantly. So This is of course a much smaller capacitor, which different dielectric material should have better properties, but it still drops off significantly. So for example, if you have your RF circuit set up, expecting 47 nanofarads, but then you give it a bias of 40 volts, you all of a sudden just have 26 nanofarads and it won't be working properly. Quite an interesting phenomenon. And if we just do a normal frequency sweep, we can see the same thing. So we just do lin sweep. Oh, no, sorry. Frequency, that's what I wanted to do. First of all, you can see that this thing actually is a capacitor for much more than that 10 microfarad capacitor. Gonna just do another autoscale again. Autoscale A, there you go. So that thing actually behaves like a capacitor throughout the entire range, just dropping down to a very low capacitance as the frequency increases due to the series and other parasitic elements of that. And at 40 megahertz we only have 6.4 nanofarads left, for example. But this is without a bias, and we can actually apply a bias. Now we can say spot bias and do, for example, 10 volts. You can see how the capacitance drops. And we can do, say, spot bias 40 volts. And you can see the capacitance drops down quite significantly. Pretty cool. We can do spot bias 0 again. Oops. Spot frequency. Spot bias 0. And there you go. Now we have a nice capacitance again. So all in all, a very, very interesting instrument to have in my collection. It's going to be, dare I say, a fun toy. These things aren't toys, but I still like calling them toys. I'm going to be doing some experimentations with the DC buses of my Tesla coil, for example. You can do an impedance sweep and figure out if it's behaving inductively, capacitively, or how well your snubber capacitors are working, for example. And honestly, lots of other experiments that I can't think of right now, because, well, if I could, I would be making them, or doing them. But if you're interested in those, make sure to subscribe, stay tuned, I will probably be making videos of those. Otherwise, I have some videos on Tesla coils, so if you're interested in those, you can just watch those. And yeah, thanks for watching, and see you in the next video. Whenever that'll be, it'll probably take another year for me to make one.